Hi everyone, welcome to this new lecture of hydraulic machines. In this lecture, we'll discuss the concept of ideal indicator diagram for reciprocating pump. So up to now we have discussed many things regarding the reciprocating pump, how the reciprocating pump is working, and what is the work done, discharge, efficiency calculation. Then after that we have discussed the sleep, then percentage of sleep. So many things we have discussed. So now we'll see the indicator diagram for reciprocating pump. For this case, we'll discuss about the ideal indicator diagram for reciprocating pump. So this is the diagram, or this is the plot, or you can say this is the graph what we got here between the pressure head and the stroke length, and this is indicates the ideal indicator diagram for reciprocating pump. So before going to discuss about the details of this diagram, we'll see the working principle of reciprocating pump, what we have already discussed previously. Just I'll give a brief idea. So if you want more details about that, you can see our previous lectures. Just here I'll just give a brief idea about the working of reciprocating pump. So we know that in the reciprocating pump we have few components are there. Suppose if I draw the diagram of this reciprocating pump, so this is the pipe is there, and this pipe, this is our cylinder, and in the cylinder we have piston and piston rod, and the crank connecting rod is connected to the crank. So this is our delivery pipe, this is our suction pipe. So this is the suction pipe is connected to the sump level, or we can say the reservoir of the water. So like from which the water need to be lifted, or from which the water need to be sucked inside the pump. So yeah, here we have that suction valve, and here we have the delivery valve, and yeah, the other diagrams I'll indicate like other colors. So suppose this is the piston which is present here inside the cylinder, and the piston is like it is connected to the connecting rod through the piston rod. This is the piston rod which is present, and the connecting rod is connected to this piston rod, and the connecting rod is connected to the crank. Okay, and the crank will be started rotating with these directions, and that crank is connected to a motor. So when the motor will be started, so the crank will be started rotating. Okay, and this is the direction of this crank. Okay, suppose, yeah, let me highlight these points. So this is our delivery pipe, and this point is given delivery valve. Similarly, here this is our suction valve, and this is our suction pipe, and this point is like sump level. We used to call this is sump level, or the reservoir of the fluids. So the fluid will be like the pipe will be connected to this one, and the fluid will be started lifting up here through this. And this is our like the point where the water or the fluid need to be delivered. And if you consider this is our center point of this cylinder, so this distance is nothing but the suction head. This is our suction head, and this distance is nothing but the delivery head. Okay, like from the middle point or from the center point of the cylinder to the distance like the water need to be delivered, that total distance is called delivery head, and the distance from this point, from this sump level point to the center point of this cylinder is called suction head. Okay, now this is our as I told you, this is this one, this is our cylinder. Okay, inside the cylinder we have this one, this is the piston, this is the piston, and this is piston rod, and the piston rod is connected to this one. This is nothing but connecting rod, this is nothing but connecting rod, and this part is nothing but crank. Okay, so at this position, if you see, the crank is in normal position, like in the rest condition, the pump is not working, it is in the ideal condition. Now when the pump will be started rotating, or when the pump will be started working, at that point, as I told you, this crank will be connected to a motor. So once you start the motor, the crank will be started rotating. So how will it rotate? It rotate in this direction. Okay, so the first movement will be of the crank will be suppose at this direction, at this point. Okay, so here it is suppose A point, this is O point, and now this one I'll take, this is B point, This is C point and this is the D point. That means this is the direction or points of the crank at different angles. This is 90-degree angle. This is half revolution will be completed. I'll tell you here. So when it started rotating, this crank will be started rotating. So suppose it reached here. Then obviously this piston which is present here, that will be moved up to some distance here. And when the crank will be reached to the B point, that means 90-degree completed. So the piston will be moved from here to at this point. Half of this path will be like in the half revolution, half path will be completed here. The B point 90-degree. Again, the crank will be moved to at this C point. That means half of the revolution completed. That means the piston when it is moving, suppose this is our left side and this is our right side. So the piston moved from left to right, and that when the piston is moving left to right, this one is called our forward direction. You can consider this is a forward direction of the piston. Now in the forward direction, it will become it will be completed 180-degree angle. Okay, if you see like it will start from the A point and it will be completed up to C point. This crank will be completed half of this revolution. Now this is our forward direction. Okay, and this is called suction stroke also. I'll tell you how why it is called suction stroke. This is our suction stroke. Similarly, like the piston will be reached at this point. The piston will be reached from the left side to right side. Again, this half revolution completed. Now remaining half revolution, that means from this point right side to left side, the piston will be started moving. So when the piston will be moved from right to left, then this is called our backward direction, or we can say reverse direction. The backward direction is nothing but we can say it will be goes move from C point to A point again through D. So 180-degree, this is 180, this is 90, this is 0-degree and 360-degree. So this is again it will reach here 360-degree or 0-degree we can say. Okay, now when it reached here, that is our backward direction, or that is called delivery stroke. That is called delivery stroke. Just I'll give again a small brief idea about that, why it is called suction stroke, why it is called delivery stroke. Now see, when the piston will be started moving in the forward direction, due to the pressure difference inside the cylinder and that atmospheric pressure. So here we know that the atmospheric pressure is acting on the fluid. So if you see, the P atmospheric will be marked here. That means the atmospheric pressure is acting on this surface level. So here the pressure which is present, atmospheric pressure, and the pressure which is available at the cylinder, both are different. And inside the cylinder, we have a vacuum pressure will be created, or that means we can say the negative pressure will be created inside the cylinder. Due to the pressure here low pressure and here it is high pressure, the water will be started lifting through the suction pipe. You see the working of the reciprocating pump, what we have already discussed. So when it will started moving, that means the water is started entering to this cylinder. So that's why it is called suction stroke, or like the we can say it is the piston is moving in the forward direction. Okay, so in the forward direction is nothing but here if you see in the diagram, it is given in the suction stroke, this one in the here. This is forward direction. Again, once it is completed half revolution, the piston reached here. Okay, it will be filled of water. So again, it will be go back, like it will be in the reverse direction. So the reverse direction, this valve will be closed. When the entering time, this valve will be closed and this will be open due to the pressure effect. Again, once the water is filled of this container, so this will be now closed and delivery valve will be opened. So the water will be goes out through the delivery pipe to outside. This is the process. So in this process, like this indicator diagram was identified, we can say, or this diagram was drawn. In the ideal indicator diagram, if you see, in the x-axis we have the stroke length and the y-axis we have the pressure head. Now the pressure head, as I told you, here we have the suction head and here we have the delivery head. And one more is there, that is atmospheric head. Atmospheric, like atmospheric pressure head. Okay, so atmospheric pressure is what? So the atmospheric pressure is nothing but the total distance from the center point. If you see, this distance will be called as atmospheric pressure head, and that will be marked as H. Okay, HATM, and here I have marked a suction from this point. Okay, but if you see the total distance, total height, how much pressure is acting on this, so that is atmosphere pressure head, which can be marked as HATM. I'll tell you like what is these things now. So this is the point what we supposed to discuss here. X-axis, what I told you, stroke length. So this also can be called as the abscissa. This can be called as abscissa. Abscissa spelling. Yeah, this is correct. And this is about the x-axis, we can say. And the y-axis, the pressure head is present. So this is our y-axis, or we still called ordinates. Okay, this is called ordinates. Yeah. Now, if you see the diagram, this is the indication of given center line of this. Okay, center line of the cylinder. So here in the center line of the cylinder, in the sense like this is the center point. Now the distance from this point, from the origin point, if you see the distance total head, the total head is HATM, which is nothing but the value of 10.3 meter. Okay, and the suction head here, obviously it will be less than the atmospheric head. So here I can write HATM is greater than HS. Okay, HATM is greater than HS. So the HATM, as I told you, that this is HATM is nothing but this is our atmospheric pressure head. This is our atmospheric pressure head, and the value of this atmospheric pressure head is nothing but it is given 10.3 meter. 10.3 meter. How we got the value also for this region is there. So we know that already. We have studied pressure formula equal to rho g h. So here P equal to the pressure, this is the density, this is the gravity, and this is the height. So when you convert this pressure into pressure head, okay, in that time you need to consider like H equal to P by rho g. So this term is called pressure head. Okay. Now what is the pressure of the like normal atmospheric pressure is there? So normal atmospheric pressure value is, we know that 101325 Pascal. Either you can convert into kilopascal, or also you can convert into bar also. So 1 bar we used to call the normal atmospheric pressure is 1 bar. So here in the denominator value of density, we can consider 1000, and the G value is 9.81. If you solve this value, we'll get like 10.3 meter. Like this value is came from by this formula. Okay, so that's why it is given 10.3 meter. Now you can see, as I told you, that this HATM is greater than the HS. SS is what? SS is the suction head. Obviously, the suction head value will be less than the atmospheric pressure head, as the pressure at this atmosphere is more than the suction head. That's why it is more. Now again, in the suction stroke, we have the pressure head will be constant. Okay, before going to explain, like few terminology also we need to consider here. I'll write that, then we'll go for the explanation again. So here we need to consider the L. L is nothing but the length of the stroke. Length of the stroke. Stroke of what? The length of the piston stroke, you can say. And HS equal to, as I told you, that is suction head. This is suction head, and similarly HD equal to delivery head. This is our delivery head. So these are the terminology are used in this, and remaining things already I told you. Yeah. Now we'll go for, first we'll discuss about the suction stroke, then we'll go for the delivery strokes. In the suction stroke, during the suction stroke, the pressure head in the cylinder will be constant. This is our suction stroke. You can see here the pressure head is constant here. Okay, and it should be equal to the that suction head. It should be equal to the suction head, that is HS. Okay, and as I told you that it should be it will be less than the atmospheric pressure head. Okay, and the pressure head in during this suction stroke, like during this pressure suction stroke, that is given at this point, that is given in the AB line, and that is which is below the EF line. You can see the EF line. Okay, and just I'm telling you like how it is represented. So this is the AB line suction stroke, or the length, suction length, that is one suction. See, if I represent in the piston, let me show you. When the piston moved from the left to right, so how much distance covered here? That is the total length. Similarly, here also if I present in this, the distance from here to here, how much distance covered for one side, like forward side. Again, it will become backward, reverse direction. So the distance covered by the piston in the cylinder. Okay, that's why it is stroke length. Okay. And next one, so here at this point, like this will be constant here, what I told. Now let's come to the delivery stroke. Delivery stroke in the reverse, like from right to left, this one, right to left. So in the right to left, if you see, here also the pressure head at this delivery stroke is constant. Okay, and that will be equal to the delivery head. That will be equal to the delivery head. And obviously which will be above the atmospheric pressure head. Now here you can write the delivery head is greater than, I can say, like H atmospheric, greater than this value. The pressure head of this value is greater than this one. And here during the delivery stroke, if you see the line which is given here, that is CD, that is CD. Okay, and the pressure head in the cylinder will be represented. So if you see, the pressure head is what? The pressure head is nothing but the distance covered in the suction stroke and the distance covered in the delivery stroke. How much? A to B, B to C. If you close this section A to B, then again this is the center line of the cylinder. Then if you come to B to F, F to C, then C to D, D to E, E to F. This closed concept or this closed line, if you see, and this is nothing but our ideal indicator diagram. This is nothing but the ideal indicator diagram. Okay, so why we are supposed to discuss this ideal indicator diagram? What is the benefit for us, or what we will get from here? We can identify where we can determine the work done, actual work done per each cycle, how much work done is happening with respect to the per second. We can calculate that. Okay, I hope you understand up to this. Now in the stroke length also, like this one, as I told you, that this is the distance traveled by the piston. So this one also is to call the stroke length is nothing but we can say the piston displacement. The piston displacement inside the cylinder, that is nothing but the stroke length. Okay, I hope you understand. Now here we'll find out the work done, the actual work done, how much is happening here. Okay, so if you have seen previous video, there we got directly the work done by the pump per second. So I'll write the formula directly. If you want to know the formula, like how we got, you can see our previous lecture. So we know that the work done by the pump, the work done by the pump per second, work done by the pump per second, I can write the formula, that is nothing but rho G A L N by is 60. And here this is we have taken for the single acting reciprocating pump into, along with this HS plus HD, both are there. Okay, now in this terminology, just I'll take a term, I'll just write here, let me write here, this is K into L into HS plus HD. So here if you see, the K is nothing but a constant, so K equal to, this is rho G A by 60. This term is constant term. Rho is density, G is the gravity, area, this is the speed by 60. This is the constant term, that's why I've written K into L into HS plus HD. Now if I write this work done by the pump per second, so K is constant term, so you can write this is directly proportional to here L into HS plus HD. Obviously directly proportional in the sense, based on the length, stroke length, based on the suction head, based on the delivery head. So it will depend, the work done will be depend upon this. Now as we have seen that the stroke length, or you can see what is the area of the indicator diagram. So let me write the next point, the area of indicator diagram. So area of indicator diagram is how to calculate. So area of indicator diagram is nothing but that how much distance covered in the suction stroke and how much distance is covered like to reach the to the delivery stroke. So suction stroke, delivery stroke, obviously we know that will be considered as the L distance, and how much distance is covered from here to here, that is nothing but B to C point. So if I write this B to C point, so let me write first here, area of the indicator diagram is nothing but we can write, so that is AB. AB is the stroke length, that is either in the suction stroke, either in the delivery stroke, same L will be there, into this is the length into height. So height is nothing but BC. So AB, I can write AB in place of BC. What we can write? BC equal to, we can write BF distance and we can write FC distance. If you add both of the things, we can get this. So BF plus BC, the total distance or total height from this point to this one. So AB, that is nothing but L. And what about the BC and BF? BC and BF, that is nothing but HD plus HS. Okay, this one we have got previously. Okay, now work done. Now we got the area of the indicator diagram. Okay, this value. Now if you put this value here, this value in this equation, okay, so what we'll get? So we can see, like, if you put this value in this equation, that means the same value we got here. Just what I meant to say, this value is calculated for area, correct, and this value is calculated for the work done, because remaining things what we have taken as a K is a constant. Now if I put this value here, that means I can write the work done by the pump, we can write it is directly proportional to area of indicator diagram, So how I got this one? Like from this correlations, from the correlation of this area point and this. Now see, area identified from here like this, the length, and this is the height. So length is L, height is HD plus HS, or HS plus HD you can write. Now work done by the pump, we know that this formula, and from that formula K term I have taken as a constant. If you will take the constant value here, remaining value is this. Okay, so now we can just put this value here, like area on here, then we can write work done by the pump is directly proportional to in the area of the indicator diagram. So this is our final conclusion, like what we want to identify from this concept. So I hope you understand this diagram, and still if you are having any kind of doubt and query regarding this, you can give a comment on the comment box. Thank you all.